professor here in electrical computer engineering. Hearing this stuff is Kent graduated so long ago I forgot where it's from. I want to tell you, nonetheless. So, like all good engineers, he started out with a bachelor's degree in engineering physics. You can share that. And math. And applied mathematics, which is really the right thing, actually. And so from the University of Colorado Boulder, which explains the current cycles, which we also share. And so Ken then went on to University of Wisconsin-Madison, PhD, spent a few years around and came here as faculty many years ago. Kent works over in the micro nanotechnology lab, making wonderful devices here to illuminate our world. And so, further ado, Choquette.
Okay, thank you for that introduction, and good morning. Welcome to University of Illinois. You are here at some surprisingly nice weather. I don't know, how many of you are visiting? Oh, okay, and how many of you are from on campus? Okay, so I'm going to talk today about, this is my introduction to nanophotonics. Turns out nanophotonics is kind of a broad subject, so this will have my bias on it, and you'll see my bias pretty quickly as we go through my presentation. But I want to make sure that I say right up front that please stop me with questions. You know, let me know as I go through this. The pictures I'm showing you here are all devices that have been made in my group. So as Professor Carney mentioned, my office is over in the Micro and Nanotechnology Lab. That's the building that is on the other side of the construction. And that building, the heart of that building, is a clean room, a facility where we fabricate devices. And so I work on compound semiconductors, predominantly gallium arsenide and indium phosphide, and build very small, tiny, as small as I can possibly make them, lasers for a variety of applications. And that's my perspective on nanophotonics. So let's get into this. So what is photonics? This workshop this week, the next 2 weeks, is on photonics, biophotonics. Photonics, anything has to do with generation, transmission, modulation, switching, applications, signal processing, storage, and detection of light. Anything to do with light. So to be honest, let's see, where do I push that? My focus is really on the generation of light. So, the focus of this workshop is on looking at bio type structures and tissues and things, and look at the light that comes off of them. I'm interested in making devices that actually emit light. Okay, so that's a different perspective, but it is something that there's a lot of overlap, because many of the things that we exploit to make devices are the very things that you will learn about in terms of exploiting how you do imaging in biophotonics. So of course, photon is part of the word photonics, and that comes about because when we at the perspective that we're looking at often in photonics, it matters about the discreteness of light. That we don't, light can be a wave or a particle, however, whatever is most convenient. And in most cases in nanophotonics, we are considering it as a particle. That we really do care about the quantum nature of light. So what is nanophotonics? Well, that's anything the science engineering of light matter interactions. So we don't just worry about light. We're looking at how light interacts with matter. And that's, of course, where the fundamental overlap comes between, say, imaging and generation of light. You might be concerned about how light interacts with tissue and how we might image it. From my perspective, I'm interested in how I can generate it on a very small length scale. But I'm interested in how the light interacts with matter, just like you're interested in light interacts with matter. So the light interaction with matter is important. So in nanophotonics, now what we're saying is that, well, this interaction is going to be over a length scale of nanometers. Now, nanometers is actually a pretty appropriate length scale for matter, because we talk about atoms. Yeah, how big is an atom? Well, if you take a hydrogen atom, we can say, well, how big is the cloud of electrons around it? Yeah, nanometers is the right length scale. And we get into the bigger atoms, of course, then the nucleus would be, maybe a few tenths of nanometers. But when we put these atoms in a solid, we know what is the lattice constant of solids. Well, they're a few nanometers, so that's an appropriate length scale. Now, when we think about light, then it depends, because it depends on what energy, what wavelength that we're considering, or what frequency. Frequency, energy, wavelength, they all mean the same thing, just different numbers to express the same concept. So if my typical wavelengths are 1 micron in the infrared, a little bit beyond what we can see with our eye. But in free space, that wavelength of light is 1 micron. Well, that's 1,000 nanometers. Okay, now if I put that through, say, a semiconductor, gallium arsenide, refractive index of 3, well, now it's 300 nanometers. So, nanometer scale, when we talk about light, it's usually a few hundreds, tens to hundreds of nanometers. So the reason why this is an appropriate length scale is that the matter can be actually a bit smaller than our light. And then what we're going to look at are how we can confine both the matter part, which is effectively electrons. All we really care about are electrons. How electrons interact with photons. That's the fundamental aspect of what we're going to be studying. So this is the outline of the next 50 minutes. We'll first talk about the photon-electron interaction at a fundamental perspective. And then, since this is nanophotonics, we'll ask ourselves, well, how can we confine the electron, and how can we confine the photon? Because we want to look at that interaction, and we want to look at it at the smallest length scales. We've got to pretty much hold the electron somewhere and put the photon somewhere and have them in the same place. Okay, so in the context of generating light, I basically want to have my electron confined, and I want to put some sort of optical confinement, basically a resonator around it to capture that photon. Okay, so we'll look at the confinement, and we'll look at 3 different approaches. Dielectric, that is to say, we just use materials in which light can be transmitted through it. Now, it seems odd that that would be a way to confine light, but that actually is a very, very effective way. We'll also have periodic means where we'll use a variety of interfaces to control it. And the last point I'll bring up is metallic. This is where we start talking about plasmons, and the plasmonics you'll hear more about this week. All right, so we'll talk about how we define the light. I mentioned that we could talk about the frequency, the wavelength, and the energy, all being the same thing. So Greek, it's always a problem when we do transfer. So wavelength, that little box is meant to be a lambda, 1 nanometer, 10 to the minus 9 meters. Usually a micron is kind of the wavelength that I'm kind of interested in, because that's typically where the band gaps of semiconductors are. And so that's why I'm interested in that. We'll see why in just a minute. But if we think about this in terms of energy, h omega, where omega is the angular frequency of light, then this formula would be that the energy as measured in electron volts. Electron volts is a very convenient unit. We don't want to measure it in terms of joules or electron volts is very convenient because we can, from an electrical engineering perspective, walk into the lab and measure things very conveniently. So typically if we measure this in electron volts, it's 1.24 divided by lambda, where lambda is measured in microns. And the 1.24 is just a unique combination of Planck's constant and the speed of light. And then finally, frequency. The frequency of light, which is measured in hertz, and that's just the speed of light over the wavelength. Now what's interesting is frequency, wavelength, and energy are all the same concepts expressed different ways to describe light, But energy and frequency don't change. Wavelength does, because wavelength depends on the medium in which the light's propagating, because light interacts with matter. Even light that interacts with matter that's transparent, like say glass or air, there's still some interaction with the molecule, with the atoms in that solid, and so light slows down. And when it slows down, its wavelength shortens. So we typically, so even though energy and frequency don't change, the wavelength will, depending on what material it's in. So when we talk about wavelength, which is a very common way to which to describe light, we'll talk about 670 nanometer light, red, or 450 nanometer, blue. Even though it's convenient, it's very common to use wavelength, we'll have to remember that usually when we say that, we're talking about light in vacuum. But when we put the light into matter, it'll be a different wavelength. So we'll need to know the refractive index. So if we now think about matter, we're talking about the interaction between light and matter, then we're going to look at these wavelengths relative to to matter. So I'm going to take then A is sort of the length scale of whatever I'm talking about. Maybe it's a chunk of crystal. Maybe it's the size of the cavity that I'm trying to capture light in. Maybe it's the size of the room that we're in. But A is sort of the length scale, and then lambda is going to be the free space wavelength. Actually, lambda is going to be the wavelength in that material. So when the wavelength is really, really big relative to the length scale, this is a condition where what we're saying is that we've taken matter and we've structured it somehow. We put in grooves. We grew layers of materials, but those thicknesses and layers or the groove size are so much smaller than the wavelength of light that that all that matters is sort of some average value. And this is the regime of, say, metamaterials that you may have heard about. Metamaterials are basically engineered materials that have unique optical properties. And what that means is that whatever it is we're doing to the material has got to be so much smaller than the wavelength that basically the light just sees it as some new material as opposed to seeing the specific grooves and so forth. Okay? Now, on the other hand, the structure that we could be talking about in our material could be on the size of the wavelength. And we'll talk about this in more detail in a little while. And this is sort of the regime of what we call photonic crystals. So this is saying that we're basically taking matter and we're engineering it at the scale of light. Now this happens a lot in biology, right? Because, for example, even though they're becoming extinct, we have these beautiful butterflies, monarch butterflies, for example, that are flying around. You ever looked at the wings of the butterfly? Depending on the angle that you see it relative to the light, it'll look different because there's structure in the wings of the butterfly wing that is basically on the same length scale as the light that we're seeing. It's a photonic crystal. It's a unique example. The peacock feathers are another example of that. That's why they, when you see them at different angles, they look so strikingly different because they're natural forms. And basically, these are structures in the material. The material is periodically modified in some way that's on the length scale of light. We'll talk about this for photonic crystals. Then lastly, we can talk about structures where the length scale is much bigger than light. Okay, I got a couple of those sitting in front of my eyes. We call them lenses. In other words, the piece of, in this case, plastic, high-index plastic, is bent in a certain way so that when light comes into, that gets focused into my eye, can be adjusted so that, overcomes the age and discrepancy that I have as a old guy, and I can see, especially when I'm trying to read stuff. So in this case, this is what we call basically lenses, geometric optics. This is sort of conventional optics because this is basically making big stuff that we're grooving, we're making shapes of lenses and things to modify how light's transmitted, but it's much bigger. So basically, we're going to be talking a lot in this area and a little bit into this area today in nanophotonics. All right, so what's an electron? Electron is a fundamental particle of matter. It is, there are only a couple of elementary particles. Electrons and photons are two of them. This is really, when you really get into analyzing this problem, this is when you see how the electron interacts with light and light interacts with the electron, you're really asking yourself how the universe works. It's pretty fundamental. So this is electron is an elementary particle. It has half spin, but it has a unique feature that we all know and love, and that is that an electron can only exist in one state. That the next electron has to be in a different quantum state. Cannot be in the same state. So this is wonderful because from this we can build a full periodic chart, all the atoms that we have in the that we know and love in our universe. Because basically every time we drop in an electron into a atomic system, it makes a new, as we fill up the shells of the atoms, we can march through the periodic chart. So this is a great deal. This is because these are fermions. This is a fundamental property of electrons. And they follow the exclusion principle. It gives periodic table of elements. Okay, now in contrast, photon is a very different critter. It's an elementary particle. That is to say, we can't take either an electron or a photon and make it into something smaller. It's the elementary particle. But in in a photon, now this is a particle that we say has a quantum spin of 1. That is to say, it's not a half, it's 1, which basically means it's a boson. Now, what's a boson? A boson is not a stupid particle. It's just a particle that now we can put as many particles in that state as we want. That is to say, when we have red light, we can have bright red light, we can have dim red light, because we can have a lot of photons that are all red. Doesn't matter. Can't do that with electrons. Electrons, when they have to be in a given system, they have to be in a different quantum state. Photons, they can, the more the merrier. Okay, that's a very different aspect. And one of these is that they don't interact with each other. Electrons, they interact with each other. They since they want to repel each other. They carry charge. They want to repel. They want to stay away from each other. They really like hooking up with something that's positive, but don't like negative other electrons. Photons don't care. They just pass through each other. They just they're completely non-interacting. Now we know that the electron. I told you that we're going to talk about it from a quantum perspective, but we also know, sometimes it's convenient to realize that they're also waves. They're a combination of an electric and magnetic wave, where the electric and magnetic waves are on orthogonal axes. This is sort of a little pictorial where we have an electric field varying in one dimension and a magnetic field varying in the other dimension. We call this transverse electric, TEM, transverse electric radiation. Okay, so, okay, what are we doing? Okay, here we go. Boson satisfy the Bose-Einstein relationship, which basically means that they can just fill all they can go into any states they want. So electrons interact with each other, photons don't. Photons are fermions, photons are bosons, electrons are fermions. So now we'll talk about the interaction between these two. So in some sense, energy is either manifest as an electron or as a photon. And what I really should say is energy is manifest either as a wiggling electron or a photon. And it can slosh back and forth between these two. In fact, there are that's one of the things we like about nanophotonics, is that we can create structures where basically the energy is a little of each at any given time, sloshing back and forth. So in some sense, the electron is interacting with a photon. So energy can either be manifest as a photon or be manifest as an electron. So we can talk about then how light interacts with matter. Okay, this is sort of taking the perspective of, well, okay, we'll take light and shine it on matter. Imaging, for example. Well, okay, there's a couple of things. One is it can be transparent. Well, what does transparent mean? Does transparent mean that the light does not interact with matter? How many think when I look out the window, I can see the stuff on the side. So is the light that's coming through that window, is it interacting with the window? Yes or no? How many say yes, light is? How many say no? Well, the answer is, of course, yes, it is interacting. Because if we go put our hand on it, we'd feel it's a little warm. Okay, so the light is coming through the window, but in fact, the light is interacting with all the atoms of the window, and in fact, it's being absorbed and re-emitted. Absorbed and re-emitted, absorbed and being re-emitted, and that takes a little bit of time. So the light slows down when it passes through that window. So even though it's transparent, the light is still interacting with it. So, well, gee, how do we describe the fact that it slows down? Well, we use that, but we define that by the refractive index. The refractive index its definition is the speed of light divided by the speed of the light in that material. So the speed of light in vacuum is c. It's a universal constant. But the speed of light in everything else is something different, depending on how the light interacts in that material. So we can use the refractive index as a measure of how that light interacts. So for example, in window, it's about 1.6. Doesn't slow down much at all. In gallium arsenide, refractive index is about 3.4. Slows down about a factor of 3. In metals, we can talk about the refractive index of metals. The refractive index effectively is 100. Actually, refractive index is actually a complex quantity. That is to say, it has a real part and an imaginary part, where the real part would be defined by the speed, and the imaginary part would be defined by how much it's absorbed. But I'm going to just consider this as a real number here. So, in opaque materials, this is basically where where light is essentially opaque, meaning it's absorbed and re-emitted, and that time that it takes to do that absorption and re-emission tells you the speed at which light propagates through that. By the way, this was a fun area that was studied by Richard Feynman, and this is one of the areas of physics that they have been able to calculate this interaction down to like 17 decimal places. I mean, it is truly one of the taking quantum mechanics and really testing it to the 17 decimal places of significant digits. I think it's one of the most exciting areas in physics today, because it's really taking our theory and making it and really and seeing how exact it is. Basically, we're just seeing how better we can measure things as we in quantum optics. All right, so now let's think about what happens when light transfers through matter and disappears. Okay, that is to say, it's absorbed by the atom, and that atom takes that energy. And the way it takes energy, of course, is one of the electrons that was spinning around the atom goes to a higher energy state. It absorbs that quantum energy. Well, this is something that was discovered at the beginning of the 19th century and was started laying the foundations of what we now call quantum mechanics. Quantum mechanics is the language of anything that starts with nano. You need quantum mechanics to understand it. It's the language of nanotechnology. So it was recognized early on that, you look out into the universe and you don't see just a variety of different wavelengths. You see discrete lines. Discrete lines. And of course, these discrete lines come about because the light is only absorbed in a quanta of the photon. Basically, that when an electron is in one energy state, it's got to absorb exactly the energy it takes to put it into another energy state. And we know what those energies are. We can write down the energy in terms of 13.6 eV divided by n squared, where n here is not the refractive index. N is used for a variety of things, so you just got to look at it in the context of which is being discussed. Here, this is just the quantum number. It's the quantum number of the system, and that allows us then to determine the right energy. So it turns out that for the n equal 2 to n equal 3 transition, hydrogen, that's a 1.89 eV, which is a 656 nanometer red line. That's a 656 nanometer photon. So when hydrogen is hanging about and we have 656 nanometer light, it's absorbed. That energy disappears as a photon and reappears sorry, as an excited hydrogen atom. That's the interaction between light and matter. So this is not a case of being transparent. This is a case of being absorbed. Now, of course, what happens? That electron goes up to high energy state, hangs out there a little while, and then spontaneously, meaning without, and we can make it come up with an average lifetime, but it decays down, gives off a photon. So basically, this is the conversion of light to matter, because it suddenly was excited matter, and then back to light. All right. Okay. All right, so let's make a comparison here. We talked about the wavelength. We can talk about electrons and photons, both as waves. In electrons' case, this would be the given by the momentum of the electron, h over mv. For the photon, it would be c over v. C over nu, where nu is the frequency. If we talked about how electrons interact in a medium, this would be the Coulombic interaction. That is to say, we have a wire. We put an electron down a wire. What's the next electron going to do? Well, it's going to be repelled by that electron. It's the Coulombic interaction. On the other hand, in terms of the photon, the interaction with a medium comes about through the dielectric constant. We know the photon interacts with light and it slows down, and we describe that through refractive index. This would be something having to do with maybe the conductivity or a variety of different ways that we could define that. Okay, so we can pursue this comparison even further. We know that both electrons and photons are fundamental particles, so we can write down we can use quantum mechanics to analyze their properties. So we can write down a wave function for them both. If we were to look at the electrons, that would give us the Schrodinger equation, where psi here is the wave function for the electron. For the photon, if we think about it in terms of waves, we'd write down the wave equation. This would be taking Maxwell's equations and taking a couple of them, combining them, and this tells us how light propagates through matter. Okay, the propagation in free space, we can talk about the plane wave. We can write that for an electron. We can write the same thing for a photon. Okay, we can talk about now if we're going to confine the electron and confine the photon, because this is where nanotechnology is relevant. We say, well, what are those length scales? Well, take a 10 eV electron. All right, that's going to be lambda is equal to 0.338 nanometers. Wow, so electrons are really small. Well, that makes sense because they're whizzing around atoms, okay? And the atoms in a solid are a couple of nanometers apart. So that means that, basically in terms of the wavelength of an electron, it's got to be at least one or a fraction of a nanometer. On the other hand, if I look at a 1.24 eV photon, lambda is 1.24 nanometers. 1.24 microns, which would be 1,240 nanometers. Question?
Yeah, what do you mean by confinement, like electrons?
So I'm going to take one of these elementary particles, and I'm going to put it in a box. Okay? And I'm going to put it in a box, and what's the size of that box? Okay, so if I'm going to put in this electron, which has a wave function, and I talk about a 10 eV electron, how big a box would I have to put it in? Well, my point here is it's going to be a nanometer or a few nanometers. In terms of confining that sucker down to its fundamental length scale, it's a couple of nanometers. On the other hand, for a photon, it's a lot bigger box. And we're going to see that when we look at interaction between light and matter, where the matter, this is the thing. The matter is going to be what we use to build our box. Because how do you build how you can build a box out of light? I don't know how to do that, but I know how to build it out of matter, right? So what's the size of that? Because I'm talking about the confinement of the electron, the confinement of the photon. I'm trying to take that that elementary particle and put it in one place. Because if I'm going to look at the interaction between light and matter, I basically got to have the light and matter at the same place. Okay, when I look out the window, the light coming through that window is, of course, all the light that is. You know, I'm not seeing light coming from behind me. I'm seeing light that's interacting between me and that window. So now what I'm trying to do is, on a nanometer scale, put it all in one place. I can go measure this. I mean, I can measure the this. God, this drives me crazy. This is lambda. This is a wavelength. I can measure the wavelength of light. I have a thing called an optical spectrum analyzer, which I shine light into it. It tells me the wavelength. Okay, so I can measure these things. So what I'm going to do is I'm just trying to give you a comparison between if I'm going to talk about the interaction between light and matter at a very elementary level. And I want to say I want to confine them to as small as possible. Then this is the sort of length scale I got to look at for the electron. And this is the sort of length scale in the right units, 1,240 nanometers. So basically, light's a big thing. Electron is very small.
So I think, I'm imagining length scale for photons is easier because of the wavelength of the light, but because of electrons, this length scale, is it something like the size of these orbitals that they travel in?
So that's the thing about quantum mechanics is we're trying to take our everyday intuition and to project onto that some meaning. So light's easy because we can say, well, no, light is easy in some because I can say, well, that's a blue shirt, you have a green shirt. Those are two wavelengths, right? But on the other hand, all that's really saying is that a photon with that particular energy hit our eyeballs and our brain called this blue, called that green. But we can say, oh, okay, that's some wavelength, and I have an instrument to measure that. An electron is the same way. An electron has an energy. It has a wavelength. So it's a wave and a particle at the same time. Now, what does it mean? I'm taking a very engineering perspective. If I want to confine this electron, I'm going to have to talk about structures that are a few nanometers. And I'll show you that in just a moment. Okay? I'm not going to talk about something that's 1,000 nanometers. It's a few nanometers. Okay.
Question.
Yeah.
So how narrow are the emission line for like hydrogen?
Okay, so that, whoops, go back to there. So if we talked about the narrowness of this line, there's lots of things. So then that would be a question of how you measure it. And so we go through all the various things that would give rise to broadening in the measurement. But fundamentally, what would determine that width is the uncertainty principle. Because time and energy are two conjugate quantum mechanical variables, which means that if I know one really well, something else I don't know. So given that an event occurred, it happened in the time scale, that means that maybe, which means that spontaneous emission, I just let it happen whenever it wants to happen, then this can be a pretty narrow line, but which means that I know very accurately what the energy is, but I don't know anything about the time. On the other hand, if I know exactly when it's going to happen, then there would be an incredibly wide energy spectrum. So the answer is, that's why we call it uncertainty principle. This is the width of this line is determined by your measurement and your quantum mechanical system. I can't, it's a.
But is it fundamentally one energy, like that, we're not changing it by measurement?
That's too deep for this for today's lecture. So there are, yeah. I think the point. So I'm going to take a very engineering perspective because that's really what we're going to be doing here, and that is so if I aim a telescope up into the universe, there's lots of hydrogen floating around. It's interacting with light. It's giving off light. and I can find this spectrum. And I can see this line, and I can look at the width of that line, and I can take the width of that line, and I can tell you what the spontaneous emission lifetime is of a hydrogen atom. Because those are the two quantities, energy and the time, that would give rise to this measurement. Of course, that light also transferred through the atmosphere, which gives rise to broadening. I use some kind of technique to measure the light, which gives rise to, so there's other measurement parts of this. So, okay. Dispersion relationships. So we're both the electron and the photon have momentum. Okay, now the electron is a little easier for us to think about momentum because it has a mass. So we know from elementary physics that any particle has velocity and a mass has momentum. Photon has no mass, but it still carries momentum. So the relationship between the energy and momentum is what we call a dispersion relationship. And it gives us a very convenient way to keep track of things. Because when we have interaction between, fundamentally, when we have interaction between particles, there are two things conserved. One is energy, and the other is momentum. So the energy, we just got to keep track of where all energy goes. And then we got to keep track of where all the momentum goes. And we know that when we have a before and after, that the energy and the momentum have to be the same. So we got to, look at how energy and momentum are related to each other for the particles. So for electrons, the momentum K is just mass times the velocity, but it's quantum mechanical property, so we throw in a Planck's constant. Anytime with quantum mechanics, just throw in a Planck's constant. Just figure out, usually do it dimensionally. I'm serious. You just figure out dimensionally. In many physics papers, they just set all these fundamental constants equal to 1. But when you do that, I think you lose track as an engineer, that bothers me because, I got to have units. On the other hand, for photons, the momentum is just going to be 1 over the wavelength, okay? So that means that the energy for the photon is related to momentum with Planck's constants with the speed of light. Because speed of light and wavelength, we know that combination of things is also energy. Whereas for the electron, in materials, now I'm talking about an electron in matter. We're often going to take a parabolic relationship between the energy and momentum. So if I plot the energy of an electron versus K, the momentum of the electron, this is a parabolic relationship that starting from zero energy, zero momentum, I have a parabola which defines the dispersion relationship between energy and momentum. For a photon, it's a different story. Now, it's basically just a linear in momentum. So these are just straight lines. And the slope of the lines here depend on the refractive index. Because that comes in because this lambda will be the lambda in the material. So if you remember, we said that that the speed of the light in the material is c over the refractive index is c over speed of light. That means the wavelength in the material is going to be the wavelength in vacuum divided by n. So n comes into this. So that's n is the slope of this. What is the we really can't talk about slope of this because it's parabolic. But what would be a number that would be that would allow us to describe how curved this dispersion relationship is? How about the mass? The mass would be, the second derivative of this curve. All right, dispersion relationship. So back to this. All right, so now we're going to try and confine the electron and the photon. So we're going to put them in a box. This is getting back to the question of why we care about length scale. We're going to put this in a box. Well, what does this mean? Well, for photon, Well, okay, now we can talk about the box. We'll talk about the dimensions of the box. Maybe we confine the photon just in one dimension. So an example system would be two mirrors that are infinite in two dimensions, but they're a certain space apart. Okay? That would be define a photon in one dimension. Or we could take the photon and define it in two dimensions. This is something that we know about all day. I should have brought my learning aid. It's a thing I got at at Disneyland. We call it an optical fiber. Okay? An optical fiber is basically a confinement of light in two dimensions. Transversely confined, it can only go down the fiber either direction. Or we can talk about three dimensions, which is basically confine a photon to be someplace in space. We can go through the same sort of idea for electron. Maybe we confine an electron into a plane. We're going to call that a quantum well. Okay? We might define it in two dimensions. We call that a quantum wire. And if we do this in three dimensions, we call that a quantum dot. Basically, we're just seeing how many dimensions we're confining it. So keep going here. So how are we going to do this confinement for the photon and electron? Well, we talked about three different approaches. We can use, for the electron, we can use Coulombic forces. That is to say, we can use essentially a combination of positive and negative charges to somehow confine the electron. Or for the photon, we use what we're going to call total tonal reflection. That is to say, we use dielectric confinement. Or we use periodic potentials. Turns out periodic potentials confine electrons in solids all the time, because if we have a solid like a crystal, like a piece of silicon, the silicon atoms are periodically arranged in a lattice. So the electrons inside of that lattice have a very specific behavior set up because of that periodicity of those ions. And it turns out that it's about, at certain energies of the electron, it's about the length scale of its wave function. So we have what we call energy band structure for solids. That happens just naturally from this periodic ionic potential. We can do the same thing for the photon. We can take a material and drill holes in it. Basically put places in the material where there is no material. It's essentially vacuum. And we'll put those holes on the length scale of light. That's a periodic dielectric or a photonic crystal. Finally, for both the electron and the photon, we can use metals to confine it. Now, confining metals for electron makes perfect sense, right? Because you basically have something that is very conductive, and you surround it with something that's not conductive. We know about wires. That's, oddly enough, a very effective way to confine light also, because I mentioned that light can be looked at as having an incredibly large refractive index. And so you can think about it as dielectric confinement on steroids, but essentially we can confine it by forcing light not to be someplace, basically in the metal. And I'll show you, we're going to talk about examples of all three of these, and we'll look at photonic and electronic confinement in 1, 2, and 3 dimensions. So that's where we're going here in the next, I can't even see how much time I got. Sorry. 5 minutes? Holy smokes, I went too slow. I will really, okay, so we'll go through this. Sorry, I got going too elaborate here. So dielectric, we're going to talk about dielectric confinement. And for dielectric, it is a Snell's law, which is we're looking at light, how light is confined. Basically, the magic of dielectric confinement is two refractive indices. Basically, two materials that have two different speeds of the light propagating through it. From this, we can confine the light. So if you analyze this problem, we can find out that in a certain case, if we have a high index material, light can't come out of it. We call that Snell's law. So there's total tonal reflection. So here is N1. N1 has a larger refractive index than N2. We can calculate this angle of refraction and ask ourselves, it greater than 90 degrees, which is to say the light reflected back into the material. It turns out that happens at a critical angle given by this inverse sine of the indices, and light is basically confined within that dielectric material. A very effective way to confine the light. Whoa. Ooh, I don't know what happened to this. This is basically looking at a planar waveguide and writing down the wave equation and solving it. Basically, we can confine light within a dielectric material. Now we can do the same thing for the electron, except now we're talking about fermions. We're talking about charged particles. So what we'll do is we'll take two different materials, not with a different refractive index, but with a different band gap. That is to say, the atoms are different in the two materials, and they're different in such a way that the electrons have, in one region of the material, have lower energy than the surrounding layers of material. So we can draw that with a potential energy. That in one material, we have certain energy levels, and then on the other two sides, let's say that those energy levels are infinite. So we have basically barriers. So we're confining the electron only to be within this material. Now, in the other two dimensions, it's infinite. It's just in this dimension that is being confined. Now, if we make this confinement on the length scale of the electron, what's going to happen? Well, basically, we can ask ourselves, well, how many electron wavelengths can fit inside of this quantum well? So we can talk about these energy levels. So basically what happens is that these levels are discretized. It falls out of solving Schrodinger's equation in this system. Why did this happen? This happened because the electron was a fermion. That when we stuck first electron in there, went into the lowest energy state. The next electron in can't go into this state. It has to go into a different state. Whereas in my confinement of light, I can put as many photons at any given wavelength as I want inside of that thing, because photons don't care. They don't interact with each other. Electrons do. By the way, what is this length scale? It's going to be a few nanometers, because the length scale, as I pointed out on the length scale of the electron, was, at 10 eV, which is a pretty high energy electron, is a nanometer. So when we look at the, go back to this. So the electrons that go into this, they have a certain wave function. Well, if I look at my photon, it's going into a dielectric structure. It has wave functions too, and they look very similar. This is to say that the electromagnetic radiation inside of this confinement is going to be described, it's going to have a certain intensity profile, which is the square of its electric field, and it's going to have a certain shape. And these are the wave functions of the light. So here are the wave functions of those quantum well. Here are the wave functions of the photon. Now what we want to do is put these things in the same thing. In other words, in my case, I'm going to take a semiconductor, make a band gap, and I'm going to make that band gap in the confinement region emit light at a certain wavelength, and then I'm going to put around it a box using the semiconductor that's the same size. So I can find both the photon that's emitted from that material and the electron that's inside of the material. From this, and this is the source of all semiconductor lasers. Inside of this guy right here that's emitting the laser, there is a quantum well semiconductor that's actually emitting at 980 nanometers. That's been frequency doubled into the green. It's the basis of every time you use your cell phone, when you've been texting while I've been giving my boring presentation, you've been using all kinds of semiconductor lasers and detectors, all relying on this technology for generating the light. Light can leak out. I gotta skip this. The example in 2 dimensions is an optical fiber, and this is the basis. This is the basis of, do I dare say this, of modern civilization. How many of you would just freak out if you could no longer use the internet? What if it just shut off today? Yeah, you think it's like air. This is what the internet physically is optical communications. You sit on your cell phone, goes up, it's wireless up to the tower, but once it hits the tower, well, at once it goes down those cables into the little box at the bottom of the towers that has no windows but a lot of air conditioners. That is when information is turned into light and goes across the into the physical infrastructure of the internet, which are these optical fiber. We can talk about doing two-dimensional confinement. This is nanowires. This is some example of some work done here at Illinois by Professor Shunlin Lee, who basically grows nanowires on the surface of wafers. So here's some pictures of these nanowires. We can talk about dots. We can do three-dimensional confinement. If we do it for optical confinement, that means we're basically taking these pieces of semiconductor and we're just making them really, really small. One way to do that is to make colloidal dots. You make them precipitate out of solution and you can get them down to the exact same, down to a specific size. What happens is now the size of the dot tells you what the color is, what the energy is that you see. So here are a couple of vials of, in this case, cadmium telluride. It's all cadmium telluride in solution, but because they're at different size, they look different colors. Controlled because basically the size of the dot is on the wavelength scale of light. We can do this in a semiconductor material. These are so-called self-assembled quantum dots. We can grow these little things, little self-assembled islands of higher bandgap material surrounded by lower bandgap material. This is a transmission electron micrograph. And the lines here you see are the atomic layers of the material. This dot now is a couple of nanometers in size, maybe 1 or 2 in tall, maybe 5 or 6 in width, which confines it in 3 dimensions. We can stick this dot inside of a laser, quantum dot laser. Periodic. We can take a material and we can now try to create periodicity to confine the light. So one way to do this with light is to just make different layers. Or we can take a layer and drill a lot of holes, where now the spacing of the holes is the wavelength of light. Or we can make three-dimensional structures where the spacing between these dielectric layers is the wavelength of light. This structure here is what I do in my research, vertical cavity surface emitting lasers. We grow, this is a side view, so here is a SEM picture. You can just make out the layers here. This is looking down from the top. From this side to this side is basically about 2 diameters of your hair, about 200 nanometers. Oh, that's not right. From here to here is about 200 microns. And 100 microns is your hair. So that's like 2 diameters of your hair. And there is, I don't know how many, maybe lasers in that area. So these are layers of semiconductor that we grow such that the light is structured in it to give us a high reflectivity cavity to make a laser. So how many of you have a laser mouse? They're kind of old-fashioned now. How many of you had a laser mouse? Yeah, you all had a laser mouse. That laser mouse is a vertical cavity surface emitting laser. And if you've done any texting today, you used 5 to 100 to 1,000 VCSELs in basically routing that information from your cell phone to to whoever you're sending it to. So VCSELs are utilized. There's about 1 billion deployed around the world, basically all within the internet. For many applications. Laser mouse was the big application. Of course, it's starting to die now. It may come back because we'll be using an inverse laser mouse for moving the cursor on a cell phone. These are used in copiers, digital information, lots of different applications. The ultimate confinement is 3D, and now, if we think about the atoms in a solid, that gives rise to electronic band structure. We can take and make structures in matter and create a photonic band structure. Yeah, and I'm going to finish up here. So we can make an electronic band gap, we can make a photonic band gap, and we can make them overlap. And if we do that, then we can do the ultimate. We can confine the photon and the electron and each on their length scale in the exact same place. And when we do that, we get new interesting phenomena that can arise. So here are some photonic crystals that we've made in my lab. This allows us to tune. This is wavelength, and these lines here correspond to the light that's being emitted. We can tune this basically by controlling the size of the structure. So we can. This is now allowing us to, as a nanophotonic engineer, I can wire up. I can design what kind of what sort of structure these things can emit, and the light's being emitted from a region here that's a couple hundred nanometers. Now, one of the things that's happening, as an example, is you can take these structures and you can functionalize this surface so that only certain molecules stick to that. And when they stick to that, they can subtly change the cavity such that the wavelength changes. And so we can use this as a sensing element to sense, literally, they're trying to get down to 1 or 2 atoms, or 1 or 2 molecules, but literally very small amounts of material to sense this. So this might be something that can be used for medical screening. The last thing is to use plasmonics, and I won't even talk about this because I'm running out of time. Church windows. This is actually an ancient technology. The Greeks knew that if they put gold particles in glass, they got really different, beautiful colors. They're relying on the fact that tiny bits of metal inside of the dielectric material created plasmons, which changed the nature of light. So when you looked at the vase in certain conditions, it looked kind of boring. But you look at it with light being transmitted through it, it looked very beautiful, gorgeous, which is the origin of many of the beautiful colors in the. This today is being pursued to try to, with plasmonics, we can shrink the wavelength of light below many hundredfold. So because I told you that effectively the refractive index for metals could be 100, that would mean that the wavelength could be 100 times smaller, which means that we get the wavelength of light down to about the same scale as the wavelength of the electron, which from a point of view of electronics, which means we can make wires that are much smaller than we currently use. So maybe this is a way we can cram more transistors closer and closer together. Because today we can make, we're having troubles with making transistors, but the bigger problem, the problem that's going to become, it's even more apparent, is we can't wire them together. We have a problem with the interconnect between them. All right, so this brings me to my summary, just a few minutes late. So nanophotonics is when we talk about the interaction between light and matter, but at the nanoscale. And you work at that very quickly when you do biological imaging because many of the features are submicron, and you're looking at the light. So you're essentially doing a nanoscale interaction with light and matter. It's inherently quantum mechanical. So one of the things, if you're really going to pursue this, you got to learn quantum mechanics. It's the language. It's if you're going to France, you got to learn French. You're going to Germany, you got to learn German. You're going to go nanotechnology or nano X, got to learn quantum mechanics. When we start to use quantum mechanics and we start looking at the interaction, this gives rise to the ability to uniquely engineer it. And I've come at this from the point of view of trying to engineer it to generate the light, to make the lasers. In this workshop, it's from the point of view of trying to see these small features. I mean, think about that. What would be to image a DNA strand? All right. Well, how would you do that? Well, you'd have to really change the interaction because the light, for example, might not be what you and I can see with our eyeball. We have to do something else. By engineering the matter, we can make interactions that don't naturally occur, and that's the whole idea behind meta materials, is to basically make new materials that have different properties. So, and my perspective, this is lots of great research and fun. Thanks for paying attention and not texting too much.
One or two quick questions. Anyone would like to ask for the better?
So in the quantum well, because each electron can only occupy one state. So is it possible that you could run out of room in the well?
Yeah, well, okay, so I give the full story.
hold on, wait a second. So, remember I mentioned that this is one dimension confinement. So that in the, let's see, go to the picture, actually. I know that first. Oh, sorry. This is a picture of quantum level. So this is what semiconductor on this side, this is two big bang, semiconductor small in here. And this dimension is confined. But in this dimension, it's infinite. So what that really means is that, yes, and when I talk about the energy related to this dimension, it can only go into the state. But I've got many states corresponding to momentum in this plane that electrons pile in there. So all it's really saying is I'm confining that in one dimension. It's when I start defining things in 3D that I'm talking about single electrons. So 3D right here. So here, this is a picture of something that's just a few nanometers tall. Well, that's 5 nanometers. That's maybe 5 nanometers tall, and maybe 10, 15 nanometers on the side. In that structure, only a couple, 1 or 2 or 3 electrons can fill this. 3 electrons, really, because of course, all the atoms of material, there's bound electrons around all the atoms that are corresponding consistent material. But 3 electrons, only 1 can fill it. Finding 3 different dimensions. Yes.
So he shows that for the helium, the energy gap is such that the photon is emitted at 650 something nanometers. So I'm just wondering, for example, in a helium neon like laser, like that they have like 630 something. So what is happening there? What kind of interaction is happening between helium and neon that we have different rates?
In the ENI, it's the helium is, okay, so hydrogen, the N=2, N=3 state is going to be red. Helium, of course, is one jump up from hydrogen. But in the HENI, helium is the atom that's excited. Neon is the atom that actually dissolves light. And in the HENI, that's why we call it a HENI laser, because it's an atomic system where we have 2 different gases. But one gas gets excited and one gas dissolves light. What happens is one gas gets excited and bumps into the other gas, which excites it, which then gives off the light. So it's a little more complicated system, but it's and it's in this case it's a manifold of states. I can't even remember that it's higher up. Well, neon has lots of it's further up the chart. So it's I can't off the top of my head remember what the manifold states are. So the answer is. Fundamentally is what the reason why you get the red light, and in fact, the HENI laser actually gives off all kinds of different wavelengths. We see red because we put in a particular set of mirrors to allow us to see the red. But you want to get infrared, put in different mirrors. You want to get green, put in different mirrors. You want to be yellow. So HENI is not fundamentally red. The HENI laser puts out a whole bunch of different wavelengths. Depends on the resonator. That's a different, that's a laser course than, say, 304, 455, or 495 here at Illinois. Oh, and that's the last slide. Some of you are students here, and I would be terrible if I didn't show this last slide. We have a whole series of undergraduate courses that do photonics, 304, 355, that should be 455. 460, 467, 495, and we have a series of graduate courses. This course teaches that. I know. Anyway, so if you are a student here, there's a plethora of cool photonics courses that you go to learn more.
Which MIT doesn't have? Which MIT doesn't have?
Yeah, that's right.
MIT's a nice little vocational school. They teach well.
That's another crazy course.
You missed my graduate course though, 564.
Yeah, mine too. It's okay.
There are more questions here. Okay.
I think you were talking about confinement between electron and photon on the same length scale. Is that the concept behind using like UCM, like quartz crystal microvalves? No.
UCM. What does QCM stand for?
Quartz crystal microvalves dissipation.
No.
Okay.
That's an acronym, but I don't know. QCL, quantum cascade laser? Yes.
When you were talking about 1D systems, you showed like how the electrons, exist at different energy levels, and you said that was really similar to the functions for light, but then you also said that light doesn't have to exist at different energy levels, it can be bosons, and they're all in the same, so why does that happen?
Okay, very good question. So I can pile in electrons in my quantum well because they can go into both additional quantized states as well as transfer states. But in matter, I can talk about the modes of light, which is basically saying, if I look at the light, what would be the shape? So if I took a light that was inside that and say I shone it on a screen, what would be the shape of that light? Well, to control that, I have to control the size of the waveguide. Size of the waveguide. So that's where so if I have a big waveguide, I have lots and lots of modes. So for example, a typical communications fiber, multi-mode fiber, has literally hundreds of wavelengths that can be transmitted down the wavelength. Well, that turned out to be a problem in some cases. And so in most high-performance interconnects, they use what's called single-mode fiber, where they very carefully craft the size of the core of the high-pitch region and the cladding around it, so that one mode can transmit down that waveguide. And they do that basically by controlling the geometric size. Because if you make it small enough, you can probably imagine, make it small enough, only one wavelength can travel. Now, so single-mode fiber is more expensive because, well, got very exacting control of that size. But from an engineering perspective, the dispersion relationship for multiple fiber is very complicated. Lots of different wavelengths can go in it. And it turns out that they all transmit down the fiber at with different refractive indices. Slightly different, but different nevertheless. So what are we doing today? You're texting, you're taking a picture, you're sending it through the internet. You're creating digital information, zeros and ones. Well, zeros and ones we use as a laser, the brighter and dimmer, That's our 0 and 1. Well, we have a sequence in time of light pulses going down the fiber. But they're going down in multiple fiber, they're going down in all kinds of different wavelengths. They travel at different speeds. So, they travel at different speeds. So, you take a pulse in time, before you decompose it into all three components, put it down the fiber, it gets the other end, it might not have the same bit stream that you started with. What is that? Well, that's crap. That's when you watch television and it freezes. That's when your phone, goes off. That's an error. So that's our one of the challenges that we have. How do you get around that? Single mode fiber. Single mode fiber though is more expensive. It's harder to use. This is where the engineering of this nanophotonics comes in, is to try to we know what, from an engineering perspective, we know what's driving our profession, at least in photonics. A lot of this is basically digital communication and how we do it, and that drives us to try to engineer the waveguides to always support the same. For example, that was more answer than you asked for.
Great. Any other questions? Let's thank our speaker. So, if anybody needs it, why don't we take a quick break? We're not about to bring anything out. Gabby, when do you want this to end?
Sometime